Hello, welcome and a very good evening. Today we want to do a little bit of DOS programming again, and this time we will do some keyboard programming. We had one episode of that very early in the series, but this time we will do low-level keyboard programming. That is, we will write our own keyboard controller interrupt handler. We already did some interrupt programming when doing the Sound Blaster sounds. And very quick note, I'm having a bit of a cold, so that's why my voice is a bit raspy. So please forgive that. Anyway, we did some Sound Blaster programming, and we needed to use the interrupts generated by the Sound Blaster to fill the DMA buffers. And I also had an extra episode on interrupt handlers and near and far pointers and stuff like that, which you can also look up, or I probably put some links in the video description. So make sure to check that out if you have more questions on the topic of interrupts. This code is relatively short, but still quite a lot to type, so let's just start. My goal here is to introduce you to the way you can do low-level keyboard programming without the bias, without the annoying habit of this that the keys repeat after a short while, but to have basically direct inputs whenever you press a key, and also to be able to query multiple key presses at once, which is very important for gaming, obviously. And this only works if you talk to the keyboard controller in the PC directly. And the idea here is that the keyboard controller is attached to the interrupt 9 hardware interrupt on the ISA bus, and that's hardwired since the very first PC, and the keyboard will generate so-called make and break key codes that you can read out from the keyboard controller, and every key basically has its own make and break code, and the make code is generated when you push down on the key, and the break code when you release the key. There's no repetition or anything, you just get told this switch is closed or this switch is open. Usually these codes are exactly 80 hexadecimal apart. For example, escape is make code 1, so break code is 81 hexadecimal, and that goes for all the other keys. There are enhanced keyboard codes for the AT keyboard from the 286 onwards, which are multi-byte codes and more complicated make and break codes, but we won't deal with those. We will simply do a very, very simple, basically not really a game, but a little drawing program where you can use the WASD keys to move around, and the left shift and the left control key, which are here, to change the color of your line that you're drawing. Very simple. You can use that and adjust that for your own games, etc. But that's basically it. So there is a very nice document called keyboard2.txt, which is sadly not available online anymore, but there is the Internet Archive with its Wayback Machine, and you can get the file still from there, and it explains in a lot of detail the programming of the keyboard controller, even the more complicated AT and PS2 style keyboard control. But we won't even go into that much detail. The important thing that you have to remember is we will be using port 60 hexadecimal and port 61 hexadecimal to talk to the keyboard controller. But that will come up in a minute. First of all, let's write the main function. We will start with a while loop as usual to get the main loop running basically, and we will have some kind of keys vector where all the states of the keys are stored, and for some symbol key escape, which symbolizes the escape key obviously, we'll ask if it's depressed, and as long as it's depressed we will keep on running, and when it's pressed we will quit out of our program basically. And the program will be a drawing program, so we will call the set graphics mode function from our VGA routines, which you already know from previous episodes, and if you don't, then check those out. And we will, upon quitting, set the text mode, and that's that basically. Inside of the loop, as usual, we will wait for the vertical retrace to make the program run at a useful speed and not faster. And that's also very standard, and that's more or less it. However, as I said, we want to code our own keyboard interrupt function, so let's just write that, and for now it will be empty. There's the attribute interrupt for the TurboC compiler, which tells the compiler that this is an interrupt handler. We will call it KBC for keyboard controller IRQ handler. Doesn't take any arguments, and it will look more or less like that. And it's always good practice to disable all other interrupts when entering the handler and enabling them when leaving the handler, so that no other driver or handler can mess up your hardware state or anything like that. Alright, how do we set the handler? That's pretty simple. We will call the setVect function, which is part of the dos.h file, I think. Let's look at the header files, and there should be, hopefully, yes, there's the setVect function, and there's obviously also a getVect function. There is, of course, also a keyboard handler already on interrupt 9, usually the regular keyboard driver, maybe with German or French or English mappings, who knows. So we will have to save that in a minute. We will define a constant called KBC IRQ, which is just 0x9, but I like to use symbolic names, and then we pass it the IRQ handler. And remember, in C, when using the name of a function, it gives you the address, so that should be fine. Also, we will need to back up the old IRQ handler, so we will introduce a variable old IRQ, and that works just by calling getVect for the keyboard controller IRQ. Very simple. Yeah, in a minute we'll introduce all those things and more. And after setting the text mode, we actually need to restore the interrupt vector. So we'll call setVect again on the KBC IRQ for the old IRQ handler. Otherwise, your machine will be unresponsive, and you can just hit reset or restart your DOS box or whatever. Okay, that's pretty neat, I would say. Now we have to fill the handler with some stuff. Also, we need to declare a variable for storing the old interrupt handler. So again, void interrupt star old IRQ. This is how you define in NCC a pointer to a function. And that's nice. And we also need to define all our constants. And I will define them all up front now, because we will need them. We first need the IRQ controller port, which is 20 hexadecimal, because every time you service an interrupt, you will have to acknowledge that interrupt to the IRQ controller by writing a certain value on port 0x20. Let's just put IRQ port here. And for generic interrupts, like with the Sound Blaster or here with the keyboard handler, it's actually by coincidence also the value 20 hexadecimal. You can read that up on stanislavs.org. There's also a page on the interrupt handler, interrupt controller, but I'll leave that out for now. This is definitely something we need to do. Then we had defined the keyboard controller IQ. This is 0x09. Then we have the keyboard controller port, and on the original PC that's 60 hexadecimal. Those things actually still exist on the PS2 and on the AT because they have to be backwards compatible. And there's a second port, it's the so-called system control port, I think it's called. It manages a couple of peripherals on the original PC. It's, I think, obsoleted on the AT, but it still works again because all the software has to work. And the important thing here is there is, I think it's explained here in the keyboard 2 txt. If we look for 61H, the old XT keyboard has a Intel 8848, which is in essence just a very primitive one-way serial interface. So all used is port 61H to disable and re-enable the keyboard on every scan code. That's the whole idea. I think there is exactly. There it's done. This port is used to acknowledge the receival of a scan code by disabling the keyboard and immediately re-enabling it. This also means that you can read a scan code as many times as you like until you acknowledge the receival. That's just how the original PC worked. So we need this, the system control port, for exactly that reason. We will also define a constant for the offset of the make and break codes, which was 80 hexadecimal. And by coincidence, the system control port keyboard controller disable function is also 0x80, which is the 7th bit. You just need to toggle that. So there's a bunch of duplicate numbers here. And do I need that? I put down one thing here that I probably don't need. No, I don't need that. I'll leave that out. It's for a later episode maybe. We defined the scan codes or the make codes of the keys. We definitely need the escape key. We also need the W key, and you can look those up here in the list. W is 0x11. And we don't store the break codes because that's just the make code plus KVC break. Then we need to define, what was it? A is 0x1E and S is 0x1F because it's right next to each other. That's very nice of IBM to design it that way. And probably 0x20 for key D. You see, this is in ascending order because it's basically the row, and you always increment one, going from one letter to the next on the keyboard. Very nice, very organized. Then we need the shift key, which is the left shift key, so I should write L shift, but I can't be bothered to do that right now. And the left control key, because you can actually distinguish between the left and right shift and control keys, which is very nice. So those are the make codes for that. Then we need to have a keys array, which I just make 256. I'm not sure how many scan codes, but it could be potentially 256 scan codes. And also because it will be handled by the interrupt handler, we need to declare it volatile because it's changed in the interrupt. Very, very important to do that. All right. I'm not going to run this right now. It will compile probably. No, there's one error. Yeah, because I mistyped the set vect. But now it compiles. I'm not going to do that because it will lock up DOSBox because our interrupt handler doesn't do much. Okay, so what do we need inside here? We need a couple of variables, bite-sized variables. We need the scan code itself. We need the state of the system controller port, and whether we have a make or break code. We assume a make code first, but we'll determine that in a second. So in comes the scan code just by reading 1 byte from the keyboard controller port. And we also have to store the system control port, what did we call it? KBC SCP, okay. KBC SCP, system control port, because we only want to toggle 1 bit, so we have to read out the actual value because the other bits control different things. And then we determine if our code is a make or a break code. So code logical and KBC break. If that is the case, then we actually have a break code. So what we do here is then to set the value that we're gonna store in our keys array to 0, which means the key is not pressed anymore. And we subtract the KBC break from our scan code because we want to write to the actual make code, because that's easier than having to test for 2 different scan codes. Basically, we map everything to the make code of the key, and that's that. And else that's actually not necessary, but for readability reasons I'm gonna set value to 1. Otherwise I can just delete that here, I think. Alright, that's that. And then all we do is we write this value to our keys structure, and then we have stored whatever there is. However, we still need to acknowledge the receiving of the scan code, so we write to the system control port, and we're doing this by toggling the 7th bit by logical ORing the value here. And we can assume that the 7th bit was 0, otherwise the keyboard wouldn't have worked, because this actually disables the keyboard. And right after that we are writing the original state back, and that should acknowledge the keyboard scan code with the keyboard controller. And after that we acknowledge the interrupt itself, and then we're done. This now should be safe to run, I think, because now we already have a working interrupt handler. We also set our interrupt handler and set it back, and it should work for pressing escape. It will be a black screen, but it should work, and it does. And afterwards I can even press some keys. It still works. Now for the actual drawing, so that we can get something nice on the screen and see that we can do more than just hitting escape. We will set a pixel at some current coordinate with some current color, which also means that we have to have some words X and Y that I'll put in the middle of the screen, smack in the middle of the screen, something like that. We need a color. Let's call something like 15, which is white in the default palette. What else do we need? It would be best, I didn't do that, but it would be best to set the keys vector to 0 completely. Otherwise, by accident, some of the keys might be set to 1 or something else, and we might have weird behavior, basically, until some keys are pressed. That looks good. Now we have to check for the keys. This will be a very simple, you can probably code up a more elegant solution, but I'm gonna explicitly test for the keys. So if I have the W key pressed, I will try to go up in the Y direction. So I'm gonna do a test. If Y is still bigger than 0, then I can return Y minus 1. Otherwise, I will just stick with Y as it is, so I don't run out of the screen. And the same we can do for the S key, which will move down as long as we are smaller than the bottom border of the screen. We can go 1 down, otherwise we stay where we are. And then we can copy the whole thing for the x-axis, for A and D. We need to do x here. And the screen dimensions is 3119. And of course we have to change for the x variable. The only thing still left is changing the color. We can do that as well. If key shift, pressing the shift key should increase the color. So we do color equals, is color still smaller than 255? Then return color plus 1, otherwise return color. So we don't run or wrap around or something. Although that could be nice, I think, having it wrap around. And here, if we are still bigger than 0, we will subtract 1. Okay, I think that's all there is. And there's the white dot. And I can now press WASD and try to draw something. Up and down works. 2 at the same time works. I can even press up and down at the same time and it will just stay. But the rollover is not perfect. For example, I can't press a third key right now. That might be a limitation of DOSBox though. I don't know, or of my keyboard. I can also press Shift to cycle through the colors and also Control to cycle through the colors backwards. Yeah, it's a pretty simple and stupid program, but you can, I think, imagine how to use this in a game to get really nice and responsive key presses. And you can of course use any keys you like. It's more difficult to do text input this way because you will receive, if the user presses down, I can hardly move 1 pixel at a time. It always moves like 2 or 3 pixels because I have to press very shortly to get exactly 1 pixel. So if you want to do proper keyboard input, you need to invest a lot more or have to disable your own keyboard interrupt temporarily and give back the control to the BIOS interrupt handler to get better key presses, basically. That's definitely a possibility. Let's press escape. But yeah, that's it, basically. So very, very simple keyboard interrupt controller handler. Very simple, disable all the interrupts, read from the keyboard port, read the status port. Maybe we should put this down here where we do the toggling. I think that's nicer. Acknowledge that you received the scan code and then acknowledge that you have served the interrupt. And that's basically it. No big magic there. It becomes more complicated when doing the AT style keyboard, and it can do some other tricks like toggling the LEDs and stuff like that are on the keyboard. But that's for another time. For now, thank you very much for watching. Make sure to check out the video description. There's also links to Patreon, Ko-Fi, etc. I'll be very happy if you could drop a coin in the hat. If you don't, that's also fine. Leave a thumbs up, leave some comments, and most importantly, share this on social media if you want to bring even more people to this wonderful retro programming. Yeah, but that's it for today. And thank you very much, and see you next time.